Understanding binary and IPs. The witty way. A coworker calls and asks, "Can you verify some IPs?" You check the network diagram and you see this. Visual noise for us humans, but the mother tongue of computers. The problem is that binary does not match our style of number pattern recognition, which is rooted in base 10. Binary is base 2. Because binary is base 2, it consists of only two numbers, 1 and 0, while base 10 consists of 10 numbers, 0 through 9. When working with binary, it's easiest to understand it as a system designed to represent the state of something, whether it's on or off, true or false, 1 or 0. Because there are only two numbers to use, there are only two possible states, A, represented by 0, and B, represented by 1. Let's take a look at some real-world examples. Here we have a lamp, and its state is on, represented by binary 1. The same lamp now has a state of off, represented by binary 0. Let's try this example again with the door. The state is open, represented by binary 1. Now the state is closed, represented by binary 0. Let's try using the state of the door and the lamp together. We start with them both in the off state. Then we change the lamp to 1 to turn it on. We continue to modify the binary states until we've tried all the combinations available. When monitoring the state of the door and the lamp separately, they each could only represent two states, on and off. Combined, they represent four different states, a combination of the door and the lamp being opened, closed, off, or on. Now let's get back to our original network diagram with the binary IPs. The IPs have been changed from binary to decimal, and while they are now easier to read and comprehend immediately, these decimal values are not the most optimal format for displaying IPs. And that is what the dotted decimal format was created to do. Now let's see how we get from binary to dotted decimal. This is the binary representation of an IP, a grouping of 32 bits that represent a specific value state based on which bits are on or off and in which position. The 32 bits are broken up into smaller groups of 8 bits. These smaller groupings are known as octets. Each bit in an octet represents a number that, when added up with the other 7 bits, can represent a number from 0 to 255, like this. Let's take a look at how this is done under the hood. Here we have the placeholders for the bits, along with their assigned value and state. To make it easier to follow along, the placeholders are being exchanged for light bulbs that serve better in demonstrating the turning off and on of bits. I mentioned before that the bits had an assigned value. Starting from the bit on the right, the value is 1. The assigned values double as we move to the left. Let's say I want to tell the computer the value of the first octet is 10, like in our sample IP. I do this by turning on some of the bits. The computer interprets the state of the bits and concludes a correct value of 10. Now let's complete the rest of the sample IP. 10.1.1.3. The bit representing 1 is turned on. We repeat this again in the third octet. In the fourth and final octet, we turn on the bits that represent 1 and 2 for a total combined value of 3. Now that wasn't so bad, was it? Take a moment to convert the binary on the screen into dotted decimal format. Practice makes perfect.